Yeah, ladies and gentlemen, welcome to this lecture on 3D coordinate systems. Today we will have the last lecture on rotations. We will discuss about small rotations and uncertain rotations. Then we will discuss all the relations between the different representations which we discussed so far. And finally, we will discuss how we derive rotations from pairs of corresponding points. So let's start with small rotations. Why do we need small rotations? The first thing is that we want to describe the uncertainty of rotations. So usually our measurements are quite accurate, let's say better than 1%, and then the corresponding entities which we derive are also better than 1% approximately. So we need to describe these small changes of the rotation best with a covariance matrix. Then we will have a look into how differential equations for a rotational motion look like. And we will see that small rotations appear always if we do estimation. So if we have some approximate values available, we want to correct those, and then these corrections usually are small, so we need to know how to describe small rotations in this case. So let's start with a rotation matrix. As we discussed it last time, we have it with rotation axis and angle. So we have the unit matrix, the sine of the angle multiplied with a skew-symmetric matrix to the rotation vector, normalized vector, plus some factor multiplied with the skew-symmetric matrix squared. And now let's assume that the angle is small. Then we know that the sine of some angle is approximately the angle itself, and the cosine is approximately 1. So that means we replace the sine of theta here by theta, and 1 minus 1 is 0, so the second part cancels. That means we are left with a differentially small rotation, which can be approximated by a unit matrix plus the small angle, differential angle, multiplied with the skew-symmetric matrix of the rotation vectors. That means the rotation direction. You see, this is actually the first term of the exponential series. But of course, this matrix is no rotation matrix. It's just 1 plus the skew-symmetric matrix. So only for differential values this will be close to a rotation matrix. Now let's have a look how these differential rotation matrices look like in more detail. So let's start with the differential rotation vector, which is the rotation axis multiplied with a small angle. So we have this relation, the elements of the direction of the axis multiplied with the small angle. And then we of course get the expression 1 plus a skew-symmetric matrix of this small rotation angle. So this rotation vector. So we have here a matrix with 1s on the diagonal and the skew-symmetric part sitting on this part. Now, if you of course take the representation with rotation axis and angle, we can take the skew-symmetric matrix as factor and multiply with the differential rotation angle. Now, how does this look like for the other representations? Let's assume for Euler angles, Rodriguez or Cayley representation. So let's assume we have the 3 Euler angles here. We'll see that this is identical to d theta. Then we have here the differential elements of the Rodriguez representation and here those of the Cayley representation. And the first thing is what we see is that the differential rotation, that means the small rotation, is nothing else than a unit matrix and the small changes of the 3 angles. You can also derive this directly from the longer expression with the trigonometric forms, which we discussed a few lectures before. That means the differential angles appear here on the off-diagonal elements. And the same holds for the Rodriguez representation. That means the differential values A, B, and C are shown here. So you see for small angles, the A, B, C and the alpha, beta, gammas correspond to each other. For the Cayley representation, we just have a factor half here, so otherwise there's no difference. That means if we have differential rotation vectors, they are closely related. We have the differential rotation vector, the differential Euler angles, the differential Rodriguez parameters, and the rotation axis multiplied with the differential angle, and they are all the same. So we can replace one with the other. That means if we do some estimation or representation of uncertain rotation metrics, we can use one of these interpretations of this small 3 vector. And the only thing is that this is different by a factor 2 for the Cayley representation, which we know you have here a small quaternion. That means a rotation represented by a quaternion with small elements in the vector part. That means it's still 1 here and a small vector dq. And this small vector dq is identical to the small or differential vector of the Cayley representation. So we have also here a very nice simple relation. Okay, these are small rotation matrices. Now let's assume we want to differentiate a rotation matrix. You have a longer expression with the rotation matrix as some factor in this expression, and we want to know how to differentiate this expression. So let's start from the basic equation, which we know R transposed is identical to the unit matrix, which are 6 constraints. And now we apply the classical rules of differentiation. We use the product rule and get the following total differential. We first take the derivative of R, which is dr, and multiply it with R transposed, plus the first part R multiplied with the differential of R transposed. And the differential of the unit matrix, this is a fixed value, so this is 0. So we have this relation. Now, we can put this part on the other side and obtain the following relation. dr multiplied with R transposed is minus R dr transposed. So if we take the transposed of this matrix, we get dr multiplied with R transposed, which is this one, except for the minus sign here now. That means this product is a skew-symmetric matrix to some small or differential vector dr. So this is a very important result, that if we take the differential of a rotation matrix and multiply it with its transposed, we obtain a skew-symmetric matrix, or other way around. If we solve for dr here, the differential of a rotation matrix is a skew-symmetric matrix to some vector dr multiplied with rotation. This is interesting because this allows us to do easy differentiation. We just replace the rotation matrix in our expression with a skew-symmetric matrix of a small vector dr and multiply it with R. Now, what does dr mean? Does it have a meaning with respect to our discussion which we had just before, to the small rotations? It should. So let's linearize at some point. And we start with linearizing the rotation matrix at the unit matrix. That means at 0 rotation. So if we take here the unit matrix, we find out that the change of the rotation matrix is just the skew-symmetric matrix. So we have here the change of the rotation matrix at 0 rotation is depending on some small differential vector dr, and this is a skew-symmetric matrix of this vector, which is this expression. And now we say, okay, we take the basic rotation, the approximate rotation, which is the unit matrix, add the differential in the classical form, and we get an approximate small rotation, which is nothing else than the unit matrix plus this dr0 as a function of the differential vector dr. Well, this we know already. This we have just shown in the previous slides. So we are consistent with that. Now, what does that mean? That means that the elements in this matrix, the elements dr1, dr2, dr3, collected in this vector, actually are a differential rotation vector. So the dr actually is a d theta, or a rotation vector normalized, a rotation direction normalized, multiplied with a differential angle. Okay, this was the differentiation close to a unit matrix. Now we look at the differentiation at an arbitrary matrix. So let's assume that the approximate values is not the unit matrix. Then we assume that the rotation which we have as approximate rotation, where we linearize, is multiplied with a small rotation to get our rotation. That means we have a multiplicative change of our rotation matrix. So let's write this down. So the rotation matrix can be approximated by the small rotation, or the differential rotation, which is I plus dr0, depending on d theta, multiplied with our approximate rotation. And if we multiply this out, we get Ra plus S of d theta multiplied with Ra. This is exactly what we assumed. That means this representation here, if we linearize it, we obtain exactly the same what we did before. But this is of course very interesting, because if we do estimation and we have an approximate value for the rotation matrix, we multiply it with a rotation depending on 3 small values which we estimated, and obtain a new rotation matrix. And because this is a rotation, this is rotation, also this matrix fulfills all the conditions for a rotation matrix. So we have no difference between the multiplicative change and the additive change if we take these relations into account. That means the change of a rotation matrix depending on the rotation vector is nothing else than the skew-symmetric matrix of the change of this vector multiplied with the approximate value, approximate rotation. So we have a differential disturbing rotation described by a differential disturbing rotation vector. Okay, now let's apply this in a first example, and we want to derive a differential equation for a rotating point. So let's assume we have here a rotation axis, and here's some point x. It rotates, let's assume with constant velocity along this path to arrive here at x prime. At the moment we assume that the velocity, the rotational velocity is the same. That means there's a constant motion. Later we can do this also for a time-depending situation. So the differential angle, that means a small angle here, d theta, during a certain time, d theta, is that what we want to derive. So the angular velocity is nothing else than the differential of theta with respect to t. It may depend on t, which we don't assume at the moment to be valid with respect to this figure. And this is usually written down as theta dot. The dot means we have a differentiation with respect to the time. And this angular velocity usually is described as with the letter omega. And then we can, of course, multiply this omega with the rotation axis, which is a unit vector. And we obtain the velocity vector, the rotational velocity vector or angular velocity vector. So this velocity vector boldface omega is in the direction of r and has the length theta dot. That means the rotational velocity. Okay, now we want to describe a small differential motion of this point x along this circular path. We start with the length of this path. So the first thing is we observe that if the direction here changes by some small angle, the length of the path is the angle of the change multiplied with the radius. Now, so we have here the small change in direction. And the question is, how long is this vector? Now let's look that r is a unit vector and x is the vector to our point. So this length is nothing else than the length of this vector multiplied with the sine of this angle between r and x, because we have here a rectangle. So if we want to derive the length of the path in a short time, it's the sine of this angle between the rotation axis and the direction to the point, multiplied with the distance of the point to the origin, multiplied with the small angle. Now this small angle, this differential angle d theta, is nothing else than omega times dt. So we can write it in this case. So we have the velocity multiplied with this small time difference. Now we put this dt here on the other side to get the velocity of x. But we also want to take into account the direction. Which direction does this point walk? It walks on this circle. So in a short instance, along the tangent of this circle. And this tangent direction is perpendicular to the rotation axis and the direction of x. So we take our length, sine, multiplied with length, multiplied with omega. This is this expression from here to here. And multiplied with the direction vector. So we take r cross x, which is the direction of some length, and divide it by the length. So this is a unit vector from here to here. And now we observe the following. We have here the division by the length of the cross product of r and x. And interestingly, this appears also here because the length of a cross product is the length of the two vectors multiplied with the sine between the two vectors. Now the length of r is 1, the length of x is here, and here we have the sine between the two directions. That means this actually is the length of the cross product, so we can cancel the length of the cross product, and we are left with scalar omega multiplied with r cross x. And now we put together the omega with the direction and we get the vector, the velocity, the rotational velocity vector. And this gives us x dot. That means the velocity of our point in 3D is the cross product of the angular velocity cross the position of the point. And if we make this whole thing time dependent, we have this differential equation. Of course, we take the right-hand rule of the cross product into account. So this is an application of small rotation vectors. And now we have a look at a second application, which is very important in our context. These are uncertain rotations. As I already said, rotations in our applications usually have a small uncertainty, let's say better than 1%. Now we have a problem. Most of the representations which we have are redundant. The Euler angle not, but most of the others are redundant. That means they have more than 3 parameters. So that means the covariance matrix which we want to use for describing the uncertainty should have a rank 3 because we only have 3 degrees of freedom. Now let's assume we start with 3 uncertain Euler angles. They may have a covariance matrix, a 3 by 3 covariance matrix. Now we derive the rotation matrix, which has 9 elements which depend on alpha, beta, gamma. And we want to describe the uncertainty of this rotation matrix. That means we put all these 9 elements of the rotation matrix into a 9 vector and describe the uncertainty of these elements using a 9 by 9 covariance matrix. Now the Jacobian of these 3 Euler angles with respect to the 9 elements of R is a 9 by 3 matrix. So it has rank 3, which we have to multiply with the covariance matrix of the 3 angles, and it's the transpose of this Jacobian. So the result will be a 9 by 9 matrix which has rank 3. This is not very good. So we would describe the uncertainty of a rotation matrix with a covariance matrix of size 9 by 9, which has rank 3, which means it has a rank deficit of 6. That means it's highly singular. And we wouldn't like to start with singular covariance matrices to describe the uncertainty of rotations. And then, of course, we have situations where the domain of our parameters is bounded. For instance, if you have angles, they are bounded between 0 and 2 pi, or they may be repetitive. So we have to be able to take these situations into account and have to discuss how to handle uncertain rotations. So let's go one step back and ask how did we usually describe uncertain entities in classical situations. So we have uncertain entities or random vectors or random variables or random matrices. We underscore those elements which we want to indicate that they are uncertain elements. And we usually describe them by the first moment of the density, that means the mean scalar vector or the mean matrix. And the second central moment, that means the covariance matrix. This is a classical representation with only these 2 elements, the mean vector and the covariance matrix. So if we have a vector x, which is uncertain, we say it's distributed accordingly, according to, which is this tilde, some arbitrary distribution m with some parameters. The first parameter is the mean value, and the second parameter is the variance, or if it is a vector, it's the mean vector and the covariance matrix. So usually we write it in this way. So it's the mean vector of x and the covariance matrix of x. Now, why are there 2 indices? The reason is very simple. If you have the dispersion, that means if you have only one vector, it's actually the covariance matrix of x with itself. Wait a moment. The covariance matrix can also be determined for 2 different vectors. So how are they related? So you have a 2 vector and a 4 vector, then you get a 2 by 4 covariance matrix. It depends on x and y, and of course you need to have 2 indices in order to describe this in short form. So the covariance matrix with index xy means the covariance of x and y, and it's defined as the expectation of x minus mu column vector multiplied with y minus mu. There should stand a transposed with a horizontal vector, so you actually get a rectangular or in special cases a square matrix. That's the reason why we have here 2 indices in order to be able to generalize this notation to the case where the 2 arguments of the covariance matrix are different. Okay, so sometimes we write this expression in the following form. So the uncertain vector is defined by the pair mean vector and covariance matrix. If we would only have this information, it's plausible, based on the principle of entropy, which I don't want to discuss, then it's plausible to assume a Gaussian distribution. That's the most plausible assumption. That means we could also say if we only know these two, we implicitly assume that this vector is following a normal distribution with mean and covariance matrix. Okay, what does this classical representation imply? Yeah, it's an explicit model, a generative model for generating random samples of our entity. So if you want to generate the ith random sample, let's say we want to generate 100 samples, then the ith random vector can be described as the mean value plus some distortion, which we take from a normal distribution usually, and EI follows some distribution M with zero mean. We make this explicit, so the distortions have zero mean, and the covariance matrix of this vector. So usually we take a routine for generating random samples from a normal distribution. And with the mean vector, I overline this in order to have a short notation. We also could say the random vector xi is the mean vector x plus some random vector ei, and ei is taken from some distribution with zero mean and covariance matrix sigma xx. So this is a classical way to describe uncertain entities. And it also gives us the possibility to generate samples for such a random variable if you want to do simulations in a program. Now, what do we do with uncertain rotations? We do the same thing as we did before. We say, we take the mean rotation and multiply it with a rotation depending on a small vector r, which actually is a rotation vector, and obtain a random rotation. So if you do simulations, you take the mean rotation, you generate a random vector r with some covariance matrix, 3 by 3, generate the corresponding rotation matrix, for instance, using Rodriguez form, multiply these two and get a sample of a random rotation. And you see, now we have the advantage that the mean rotation is described in some way, for instance, by the 3 by 3 matrix. We don't care about how you represent it. The best is with the rotation matrix. And we describe the uncertainty by the covariance matrix of this 3 vector, which is the 3 by 3 matrix, which is fine because we know the rotation has only 3 degrees of freedom. That means the covariance matrix has full rank in general. So we could write an uncertain rotation is described by the pair mean rotation and the covariance matrix of a random rotation vector r. Usually this stochastic vector is small, so let's say below 1%. So this is a reasonable way to describe it. If you have larger deviations, things are more complicated because, for instance, if you have random variations which are larger than 10 degrees, 20 or even 50 degrees, then you need to have a different representation than that what I discussed here. Now let's assume we have 2 uncertain rotations and we want to concatenate them. Of course, the concatenation is also uncertain. So let's assume we have an uncertain rotation R1 and an uncertain rotation R2 with the mean rotations and the covariance matrices. And we would like to know the distribution of the product of these 2 uncertain rotations. Of course, this is also described by the mean rotation, the product of these 2, and some covariance matrix of some vector r. And the question is, what is the mean rotation if we take the product, and what is the covariance matrix of the combined, the concatenated rotation? And what we will see immediately is that the mean rotation is nothing else than the product of the two means, which is quite plausible. And the covariance matrix of the combined rotation is the covariance matrix of the second rotation plus some transformation of the covariance matrix of the first rotation. And it goes with R2, which seems to be plausible. But we need to prove this. So we have a very simple expression for concatenating uncertain rotations. We want to show how this can be proven. So let's assume we have this relation R equals R2 times R1. We again take the total differential, which is dr. Now we take the differential of R2, which is dr2 times, and then we multiply it with R1. And then we take R2 and multiply it with the differential of R1. Okay, now we take our result from the first slides of this lecture and say that use the relation between the dr and the skew-symmetric matrix to some vector. So the dr here for the combined rotation is a skew-symmetric matrix of some differential vector r multiplied with the rotation. The same holds for here, but of course for the second rotation, so we have the skew-symmetric matrix of dr2 multiplied with r2, and the whole thing multiplied with r1, plus r2 multiplied with the skew-symmetric matrix of dr1 multiplied with r1. Okay, we would like to know the dr. Okay, let's first eliminate the r. We multiply from the right with r transposed, which is R1 transposed, R2 transposed, so we get SDR, SDR2, because this is just the transposed of this one. And here we get R2, SDR1 multiplied with R2 transposed. So this is fine. Now we have this SR in the middle, and if we want to do variance propagation, we would have all these elements explicitly on the right-hand side of some matrix vector multiplication. So we need to look what this expression actually can be simplified. And then we remember the last lecture. This is R multiplied with the skew-symmetric matrix multiplied with R transposed. And this is the skew-symmetric matrix of R of A, R multiplied with A. So we have the skew-symmetric matrix of dr is the skew-symmetric matrix of dr2 plus the skew-symmetric matrix of R2 times dr1. This looks good. We still have the S's there, the skew-symmetric matrix. But of course, the skew-symmetric matrices all depend on the three elements, let's say the upper right three elements. So if they have to fulfill dr equals dr2 plus r2 dr. And now we have exactly that expression which we need for doing variance propagation, for deriving the covariance matrix of R as a function of dr2 and dr1. And we easily see that then we obtain this result which I told before. Just a remark, we can do exactly the same if we use quaternions. So you take the mean quaternion, then you take a small quaternion, which is 1, and a small vector u, which is random. You normalize this vector and obtain a quaternion. So if this is a unit quaternion, the normalization guarantees this is a unit quaternion, so the product is a unit quaternion, which is uncertain. And you describe the uncertainty of this quaternion by the covariance matrix of this parameter u. You see, we use here the Cayley representation for this value. And that means we can represent a rotation by a mean quaternion and the covariance matrix of the Cayley parameters. We could also take different parameters for, if you have here m half, we could also do the same thing. So this is also, this what we discussed for rotation matrices can be extended to the other representations easily. Okay, this finishes the discussion of our rotations, the individual representations and small rotations. And now we want to have a look at the relations between these different representations. So what did we see? We had 7 different representations. An orthonormal matrix are Euler angles, axis and angle, the exponential of a skew-symmetric matrix, a quaternion, the Rodriguez parameters, and the Cayley parameters. So how are the relations between them? The rotation matrix, of course, can be derived using the equations which we derived. The Euler angles are a little bit off the road in this comparison, but we will come to that back in a minute. And we take these different representations. So let's have a look at this table. I hope you can see this. We have here the rotation vector, here the axis and angle representation with r and theta. We have here the quaternions, and here the Rodriguez representation, and here the Cayley representation. The first thing is we see that the rotations here can only be represented if they are not 180 degrees. And what we see in this table is how the individual parameters of these 5 different representations can be derived from the others. So, for instance, the rotation vector theta can be derived by just multiplying the rotation axis with a theta. Or inversely, if we have the theta given, we can derive the rotation direction by normalizing this vector, and the angle is nothing else than the absolute value of this vector. Here we have the relation between the axis angle and the quaternion representation. So this is the unit quaternion which we discussed. We have the cosine theta half here, and the rotation axis multiplied with the sine of the theta half the angle. Here, in this case, we have the Rodriguez representation. Actually, we only look at the angle here. So we have here 2 times the arcus tangens of m, absolute value, divided by 2. So the arcus tangens of some entity is, if it is small, it's approximately the entity itself. So for small angles we get m divided by 2 multiplied with 2. So for small angles the length of the Rodriguez vector is identical to the rotation angle. This is good. And finally, we see that the Cayley representation is nothing else than, instead of normalizing the length of the vector of the quaternion, we normalize the vector to that the scalar part is 1. So these 3 elements we discussed already: the rotation vector, the unit quaternion, and the Cayley representation. And now if we look at the differential angles, we remember that the rotation vector, the differential rotation vector, is identical to the differential Rodriguez parameters and to the differential Euler angles. Here we have the relation to the Euler angles. So for small angles we can always say, if we have alpha, beta, gamma, and alpha, beta, gamma are small, they are approximately the rotation vector. And for quaternions we have just this factor 1 over 2 as a relation to our rotation vector, because this is plausible because we have the rotation represented with a double multiplication. So we multiply our point quaternion from left with q and from the right with q power minus 1. That means we have 2 rotations, and that means we actually do a double rotation with half the angle, which is plausible. Now, all these representations have their pros and cons. So what are these representations useful for? What we already discussed is that the rotation matrix, of course, is useful as exchange format. We discussed this, and of course it's a basic entity which you use if you want to transform points. Then if you use Euler angles, they are quite interpretable for if they are small angles. For large angles it's not really comfortable. If you have an axis and angle representation, it's quite useful because it's interpretable, and if you have instruments where the axis is somewhere in arbitrary direction, you can actually link this to the axis and angle representation. Then we have the exponential representation. It's the most compact form for the rotation matrix, and it's interpretable because we have the direct relation to the axis angle representation. The other three elements have no trigonometric terms. The quaternions are directly interpretable, and they have no singularities. So we can use them in all cases. While the Rodriguez and the Cayley parameters have singularities. They are not useful for 180-degree rotations. And we have the nice property of the Rodriguez representation that the changes, small parameters of m, correspond to small Euler angles or to small elements of the rotation vector. So this is the overview of all these rotations. And we now want to know how do we get rotations from given data. This is our next topic. So let's assume we have some points given and we rotate them around the origin. And the question is, how can we derive the rotation from the points before and after the rotation? We discussed the general equation, general scheme already in context with the Cayley representation, but I want to look at the case once more. If we have only a few parameters, a few points, then there should be more simple equations. So let's assume we have the following situation. We have a set of corresponding points, A prime and A double prime, B prime and B double prime, and they are related, for instance, by if you rotate A prime by R, you get A double prime. And unknown is the rotation matrix. And we want to derive it from these two sets of vectors. The question is now, how many of these corresponding points do we need? 1? Is that sufficient? 2? Seems doable. 3, certainly. Okay. Each point is represented on the sphere is represented by 2 values, longitude and latitude. So it's 2 parameters. So if we have only A prime and A double prime, we have only 2 constraints, though these are 3 vectors. That means we will not be able to have a unique solution if we have only 1 point pair. But if we have 2, it should be possible. So at least 2 points are necessary. In the following, I want to talk about 3 cases. I start with 3 vector pairs, orthogonal and non-orthogonal. Then I talk about this case with 2 vector pairs. And I also want to discuss the case if you only have only 1 pair. And then, because these data may be uncertain, we will not obtain matrices which are rotation matrices. They are only approximate rotation matrices. And that means we need to discuss how to approximate a given matrix by a rotation matrix. So let's start with the case where we have 3 orthogonal pairs. So let's assume we have a tripod here. It rotates, and before we have the 3 vectors E1, E2, E3 in arbitrary direction, prime, and E1, 2, 3 double prime after the rotation. Now, what we observe is that if we put these 3 vectors before and after the rotation into a matrix, we get a 3 by 3 matrix, which are actually the columns of a rotation matrix. So we have two rotation matrices built by these given entities, R prime and R double prime. So they contain the three elements as columns. Now, if we multiply the three columns of the first tripod with R, we get the three columns of the second rotation matrix. So E1 prime multiplied with R is transformed to E1 prime, etc. That means we have a relation. The R double prime is nothing else than R prime multiplied with our unknown rotation. Okay, that's easy. We multiply with R prime transposed from the right and obtain our R, which is nothing else than R double prime, which is the columns of E1 to 3 double prime, and the transposed matrix, which is E1 to 3 prime transposed. So this is very easy. And just a remark, if the first tripod is a right-handed system, X, Y, Z, and the second one is a left-hand tripod, this mirroring is visual in the rotation matrix. That means if these are opposite systems, then R will have determinant -1. Now let's assume we have three arbitrary vectors, let's say these ones, and we rotate them. Then of course we have a matrix A double prime, which has these three columns, and we have a second matrix A, B, C prime, which is A prime, and we see that if we multiply these vectors A prime with R, we get A double prime, etc. That means we have the same situation as before. Instead of the rotation matrices A prime and R prime and R double prime, we now have matrices A prime and A double prime, and we get the same result. Of course, we can't take the transposed here, we have to take the inverse. So A double prime multiplied with the inverse of A prime is the rotation, if the data are perfect. That means we have this matrix multiplied with the inverse of this matrix. So this is very easy, and of course it assumes that this matrix A prime, that means the three matrix composed of these three vectors, is not singular. If the three vectors are coplanar, then this matrix will be singular, then we will not be able to use this equation. And of course it may include mirroring, so if we start from this situation to, let's say from here to here, then this contains a mirroring, and this is of course kept in R. Now let's assume we have only two pairs, like this, and rotate them. Can we solve that? Yeah, this is quite easy. We assume, of course, that these two pairs are not the same or not parallel. We just extend this two directions with a third direction, which is certainly not within the plane of A and B. So we take the cross product. And then we can use the previous case. So if we take A prime and B prime, and calculate C prime as the cross product of these two, we get three vectors which are not coplanar, and be the same for the double prime vectors, and we can use this expression. So this is easy. And of course, because we only started with A and B, and the cross product is taken here in both cases, the result will have no mirroring. Finally, what is the rotation if we only have two vectors? So let's assume we have the pair A and B. I loosened the notation and didn't say A prime and B, A double prime, but say A and B. So let's assume we have here the sphere, and you have here the point A and here the point B, and you want to have a rotation which brings A to B. There are many paths. So you can, for instance, go from here around this circle. That means rotate the sphere such that A walks to B. We could also go the other way around, from here to B. We could also go on this circle or on this circle. And of course there will be a shortest path between A and B, which actually is defined by the great circle. This is this red line. That means if we say the rotation between A and B is that rotation which is the rotation along the great circle through A and B, we would get a unique solution. And the unique solution is given here with this expression. I don't want to prove it. So you actually take the vectors A and B. The tilde just means that if the vectors A and B are not normalized, you first normalize them. So all these vectors A and B tilde are normalized vectors. And if you take this expression, you get a rotation matrix, which rotates A into B along the great circle. You can show that if you take the rotation axis AB, so AB, the rotation axis is A cross B, and you put the rotation, you apply the rotation to that axis, it's actually invariant. So you can prove this by explicit multiplication. Okay. Now we have seen that we can derive the rotation matrices from 3, 2, and 1. And of course we have the case of more than 3 corresponding points. And we did this already using the Cayley representation. Now, what happens if the matrices which we derive are not rotation matrices because our given data are uncertain? So especially in this case and in this case. In this case we assume that they are approximately orthogonal, so we get an approximate matrix which is approximately a rotation matrix, and of course here again. So what we need is a rotation matrix which is as close as possible to the matrix Q, which we actually get from the observations. So there's an interesting theorem which says something about the best approximating orthogonal matrix. So let's assume we have an arbitrary regular matrix Q with a singular value decomposition. Q is a product of U, S, and V transposed. U and V are orthogonal matrices. S is a diagonal matrix. And we just take this diagonal matrix out and get an orthogonal matrix R, which is the product of 2 orthogonal matrices. Now the nice property is, which you can prove, that R minus Q is smallest in the sense that if you take the sum of the squares of the differences, that this is smallest. That means the Frobenius norm of the difference of R and Q is minimum. You can find the proof in our own. The proof is a little bit lengthy, therefore I omit it at this place. Now let's have a look a little bit more. So the singular value decomposition is the product of orthogonal matrices, not of rotation matrices. So U and V have determinant plus or minus 1. And then we have the diagonal matrix S, and this is guaranteed to have positive entries if Q is regular. Now let's have a look at the sign of the determinants. We take the determinant of Q. It may be positive or negative. It need not be plus 1 or minus 1 because we have still the S in the expression. But it has a positive or negative sign. Now we take the sign of this product and cancel the determinant of S. Because the determinant of S is positive, the sign of this product u multiplied with v transposed is staying. So we have the same sign of the determinant as q. And now, of course, u multiplied with v transpose, the determinants, which are plus or minus 1, gives the sign of r, which may be plus or minus 1. So we have the following result. If the matrix Q has a positive determinant, it need not be 1, then R, which we estimate from this method, is a proper rotation matrix with determinant plus 1. Otherwise, the transformation contains a mirroring. These were rotations from 1, 2, or 3 pairs of points. And if we have more than 3 pairs, we already saw an example using the Cayley representation in the last lecture. We will see there is a faster algorithm in the context of motion estimation. We will see this in a later lecture. So let's just summarize. We are now finishing the discussion about rotations. We have seen there are quite some different representations. And the task of an engineer is to choose the adequate one for your application. There is no unique advice which I could give you. The second is that we are able to represent the uncertainty of a rotation using a equivalence matrix of 3 parameters. We showed this for rotation matrices. We saw that this could be extended to quaternons, and it can be also, of course, transferred to the other representations. And finally, we saw how to derive rotation matrices for pair of directions, which is quite useful if you want to get approximate values for some iterative procedure which requires approximate values. So this closes the rotation section. And in the next lecture, we will start with spatial motions and similarities, and I hope you are back again. Thank you very much.